Now this is a harder problem because I'm going to lead you astray early on and see if you can figure out the right way to do this. The problem is that you've given a input waveform, and it's this flat top boxcar waveform. And that rather simple waveform is going into a system. And you know what that system's impulse response is? That impulse response is also a flat boxcar type response from -4 to +4. So the question is, what does our output look like? Now, since this is a Fourier transform lesson, it might not be unreasonable to firstly try to find its x of omega. And sure enough, we can find that right here. It's a pulse. And here our tau is 4. So therefore, our x of omega must be with tau equaling 4. Is there anything else we need to know? No, it's a height of 1. So therefore, our x of omega is going to be 2 sine of 4 omega all over omega, which is a kind of a sinc. Let's graph that versus omega. We need to first determine what is it at its 0 point. Well, at 0, remember we can't substitute in 0 directly or else we'd get 0 over 0. But we know that sine of a small value is just that small value. So as omega gets smaller and smaller, that becomes 2 times 4 omega over omega. This is only true for small omega. The omegas cancel, and we're left with an 8 value. So then as we continue to increase omega, we can see that it's going to hit a 0 point, and it will hit a 0 point when the argument to sine is pi over 2. And that's because we know that sine of pi over 2 is equal to 0. So if we want to find this first 0, we just try to match this pi over 2 term with this 4 omega term. We say, where is 4 omega equal to pi over 2? Well, it's equal to it at omega equals pi over 8. So we can plug that in. And you can continue to play this game over and over, and you'll see you get something like this on this side and something like this on that side. Since our h of t is the same waveform in the time domain, it must also have the same waveform in the frequency domain. And when we multiply them together, that means that our y of omega must be equal to the square of this. So that would be 4 sine squared 4 of omega over omega squared. Now, I'm going to tell you, I know what's on that transform sheet. There is nothing at all that looks like that. If you were to graph this, we'd have 8 times 8, so it'd start off pretty high at 64. And then it would go down, and you can see that it would have to go down to 0 at pi over 8. In fact, it would sort of curve down there. That's not obvious at first that it would curve. You'd have to plot it to see it. But that's what the y of omega would look like. And these curves gradually go down to 0. And the problem is that really doesn't help us finding that inverse Fourier transform, since it doesn't exist on the sheet, and there's really not much intuition to be gained by looking at this waveform. So sometimes it's important to use things other than transform methods. And you already know how to do this convolution. Use the flip and shift method. So to use the flip and shift method, you start off by constructing your h of minus t. So this is now just a review. Instead of being apparently a problem about Fourier transforms, it looks like it's a review of the graphical method of convolution. Our h of negative t is the same thing as our h of positive t. Just hang with me because we'll eventually get back to Fourier transforms in a moment. So this looks like the same thing. And now we're going to start to flip and shift. So if you remember how to do that, we're going to start to solve for what is y of 0. And to do that, we're not going to shift it at all. We're just going to overlay our h of negative t on top of our x of t, do a point-by-point multiplication, and multiplying this by this gives you all zeros out here for less than -4 because you're multiplying 0 by 0. For values greater than -4 in this region, you're multiplying 1 by 1. That's a value of 1. So that's a 1. And in fact, you end up pulling out your original waveform. Your y of 0 is the integral of this waveform everywhere. It's the area underneath that curve. So it's got a length of 8, a height of 1, so its value will be 8. Let's find out what y of 1 will be. When we get to y of 1, we take this h of t and we shift it 1 to the right. So now it pops up at -3 and it goes down at 5. And when we multiply x of t by h of, that's a multiplication, 1 minus t, when we multiply those two guys together, we get something that's 0 all the way to -3, because before -3, this thing is 0, so we're multiplying zeros by 1s up here and we get 0. Starting at -3, we multiply 1 by 1 and it pops up. But it'll pop back down at 4. For values greater than 4, we're multiplying zeros by maybe 1, maybe 0, but it's still going to be a 0 times this, so that'll be 0. And now we integrate this area and we see this is 7. And by the same reasoning, we can shift this further and further to the right or to the left. Let me do another more extreme shift. Let's solve for y of 4. So that gives us h of 4 minus t. That looks something like, now we've shifted it really far to the right, 0 to 8. And when we multiply our x of t times our h of 4 minus t, now we end up with something that's all zeros because of this, and then all zeros after 4 because of that, and we end up with something that only has an area of 4. And maybe it's clear that as we continue to shift this guy further and further to the right, eventually, for y equals 8, we'll get 0. I'll do that quickly. If this is obvious to you, just skip over it. So our h of 8 minus t is something that comes up, if we add 8 to both these sides, now it comes up at 4, comes back down at 8 plus 4, which is 12. When we do a point-by-point multiplication of this with our x of t, we end up with zeros everywhere. And so the integral of that will be 0. And in fact, it will be the same thing for 9 and so on. Meanwhile, if we shift it to the left, we also get 7. See what happens there. We want to find what is it for a -1 minus t. So we shift it to the left by 1, so this becomes a -5, this becomes a 3. When you multiply this by our x, we end up with something that pops up at -4, and then it's going to pop down at 3, because this is zeros after 3. So this area is 7, and by the same reasoning, y of -4 will be 4, y of -8 will be just when it pops down to 0, and for values less than -8, it'll stay 0, so if we were to graph it, it would look like that triangle waveform. Height of 8, and pops down at -8 through 8. Now here's why this problem that apparently had nothing at all to do with Fourier transforms actually does. Let's take a look at what we saw before, our first attempt. We know that the convolution of these two waveforms, we know that the Fourier transform of these two waveforms are shown below, and so the convolution of these two waveforms has to be the product of the two waveforms in the frequency domain. And so y of omega is this. But over here we found that y of t is this. So what we did is just derive a much more complex Fourier transform pair that's not on our tables, but we derived it using our tables. We found out that this triangle wave has a Fourier transform of this odd squared sinc waveform. In other words, here's our latest and greatest Fourier transform pair, that a waveform that looks like this, and changing these 4s into the more general A, has a Laplace transform of A sine squared A omega all over omega squared. That's pretty cool. Ready for one last example?